Since on Friday we didn't actually talk about the test, is there anything you want to know about the test? Let's see. I guess I should probably say a few words about the test in general. First problem. The majority of people did not get it, and the reason for that being is that you forgot to realize that ln of 2x, 2x has to be positive, and so that's where you actually are limited from 0 on and not from minus infinity on. Let's see. Problem number 2. Some of you remember the answer, and so, it just magically showed up there. But,
wait, we've had this problem before? I thought you said it was brand new.
It was brand new, but it was in the outline.
Oh.
And so, when I gave you the solutions for the outline,
That was the one I gave you.
So, let's see. Do you want to see number 2? Okay. So, the hints that I was trying to give you in class should have helped you solve the problem. But,
Use extra.
Yeah. And so we're supposed to find the slope of the tangent line, or we're supposed to find the points where the tangent line has a slope -1. So if you take derivatives in both sides, implicit differentiation, you'll have 2xy squared plus 2x squared y dy dx plus y plus x dy dx is equal to 0. Does that make sense? Now, due to the fact that everybody did so well on this problem, I decided to give you like 8 or 7 points or 8 points just for actually coming up with the derivative, even though that wasn't really the hard part about the problem. But I figured if I don't give you a good portion of the points for just taking the derivative, then I'll probably just end up actually not giving you many points, period. Anyway, the point is we're trying to find the points for which the slope of the tangent lines are -1. And so a lot of you, what you did is actually solve for dy over dx, which is one way of approaching things. But the key idea is that dy over dx is equal to -1. And so this is just 2xy squared minus 2x squared y plus y minus x is equal to 0.
Oh, so just don't even...
Now, the idea is that these points have to be on the graph, and this is what I was telling you in class about the fact that you have to end up with a system of equations. And so what you're actually solving is a system of equations of this nature. Is this making sense?
What did you just do?
What do you mean?
Numbers and variables.
I said you have to solve this. I didn't say it's solved.
No. When you went from 2xy minus 2x squared y, plus y minus x, you factor out the 2, but what happened to the y and the minus?
I didn't factor anything.
Oh, never mind.
It's a system of equations, hence 2 equations.
Oh, yeah, it's original problem.
The original function. The point is it has to satisfy both of them.
Oh, okay.
Right? Now from the top one, you can observe that you can factor out a 2xy, and you're left with a y minus x plus y minus x is equal to 0. And so this becomes 2xy plus 1 multiplied by y minus x is equal to 0. And if I still work on this a little bit, this means that xy has to equal minus a half, or y is equal to x. Does that make sense? So far so good? Yeah? Okay, so now if xy is equal to minus 1/2, put it into the second equation, excuse me, the second equation, and you end up with 1/4 minus 1/2 has to equal 2. Well, clearly that can't happen, right? Yes? So that's a no, and so if y is equal to x, then x, let me write it out, I guess. So if y is equal to x, then I have x to the 4th plus x squared is equal to 2, which is equivalent to x to the 4th plus x squared minus 2 is equal to 0. And if you remember your pre-calculus, fair enough, this is x squared minus 1 times x squared plus 2 is equal to 0, which means x squared has to equal 1, which means x is equal to plus or minus 1, which means your points are 1, 1, and minus 1, minus 1.
Did anyone get this whole problem right?
No.
Not one single person? I was going to say kudos to that.
Well, I mean, technically, there were some people that got very close to it. For those of you who actually got close enough, a popular answer was to acknowledge that x was equal to y without actually looking at the other part of 0. So if you actually solved, some people actually solved for dy over dx and set it equal to negative 1, and then when you actually have it as a fraction, you can actually factor out a 2x y plus 1, and you just cancel them out, which to some extent it's okay because we know that can happen in this instance, but anyway. Is this making sense? Yeah? I did tell you in the class that this is basically the hardest problem in the test. And I just deemed that would be a nice problem to put on the test, considering it was on the outline, but nobody actually asked me about it, which meant that you are so versed at solving it.
It just happened to be the one I did.
The only one, right?
Yeah, the only one. Every single one. Except that one.
Okay, what else? 4? Okay, yeah, before I get to 4, is there any question, is there any reason to talk about anything from 3? So 3 had 5 parts, right? So you had to find derivatives, 5 derivatives. Let me just say a couple of words. Last problem seemed to be very creative for a lot of you. You're asked to find the derivative of cosine inverse, and so the idea is. Oh no, was that it? Oh no, 6 was the one that was interesting. Yeah. Okay. Let's see. C. You all you have to do is actually apply the chain rule. Some of you actually applied logarithmic differentiation to it, which there's nothing wrong to it. It's just a lot more work. You just have to keep in mind if you do in fact apply logarithmic differentiation to come up with a derivative, then you have to make sure that at the end you actually multiply by the original function. You can't just say it's ln of 2 to the t sine of 2t, so you have t sine of 2t times ln of 2 and work out. It's number one. Another thing that I should point out that I've seen on some of your tests is that ln of 2 is an actual number. The derivative of ln of 2 is 0, not 1/2, as I've seen in some of your exams. And so when you do apply ln both sides and you take the derivative, you only have product rule twice. You don't actually have it 3 times, as I've seen in some of your exams. But that's basically the idea. D, the only way you could have possibly solved it is actually using logarithmic differentiation. There was no other way to solve it. And this is where I was telling you about the fact that you have a function to a function. The only way to solve it is you actually apply ln both sides. And then, again, at the end, you have to make sure to remember that you have to multiply by the function. Yes?
How do you simplify A? I think we've gone over this problem before, but...
Okay, x divided by the square root of x squared plus 1. Right, so when I take the derivative of this, I will end up with, I need to look at it, I notice it's a quotient, right, so I need to apply the quotient rule. So I'll have the derivative of the top times the bottom, so I have the square root of x squared plus 1, minus the derivative of the bottom, which is going to be 2x divided by 2 times the square root of x squared plus 1, times x, all divided by the square root of x squared plus 1, quantity squared.
These cancel out.
So far so good? What cancels out?
The 2's.
The 2's. Yeah. And now you have a fraction on the top, and you have a denominator, right? So if you want to simplify, the first and most common thing to do is to get to a least common denominator. So what would the least common denominator be for the numerator? So I have the square root of x squared plus 1, quantity squared, minus x squared, divided by the square root of x squared plus 1, cubed. Does that make sense? Yeah?
Is there anything else to it?
Well, what's the square root of squared? What's the square root squared? You have x squared minus 1 minus x squared, x squared plus 1, sorry, minus x squared divided by x squared plus 1 to 3 halves. The x squares drop out, so you're left with 1 over x squared plus 1 to 3 halves.
How do you get b 3 halves? The exponent.
Laws of exponents. What is by definition the square root of x?
1 over 2 square roots of.
Not the derivative.
Wait, what you said?
I said what is by definition the square root of x using laws of exponentials? It's just x to 1/2.
1 over square root of x. No, it is the square root of x.
I just wrote it as x to 1/2.
Yeah.
Right? So you have the square root cubed. So you'll have the quantity to the power 1/2 times 3. So it'll just be 3 halves.
Okay.
Of course, if you would have that would have been an acceptable answer as well. That's not really, the issue. Anyway, the one thing that you should notice and you should take out of this particular problem is the following. And by the way, if you didn't completely simplify, I took 1 point off just so, it's not necessarily that it's life-changing, but it's just so you, keep an open mind about simplifying. Why is this actually very helpful? Well, remember what we talked about on Friday, right? We started looking at critical points, which is where the first derivative is 0, right? So if you actually work it all the way out, and you come up with this particular answer, clearly the first derivative is never 0, right? Not only that, and we're going to find this out on Wednesday, we're going to actually be interested in the sign of the first derivative. So we're going to be interested in where the derivative is 0, when is it positive, when is it negative, when is the second derivative 0, when is the second derivative positive, when is the second derivative negative. Well, if you just look at it right here in this particular form, you notice that the denominator is always positive, which means this entire fraction will always be positive, which is not something that you're going to observe just by looking at it on the top. Okay? Also, as I said, we're going to look at the second derivative, so I would like to be able to take the second derivative. Do I really want to take it from the above? Just think about it for a second. What would it entail to actually take the derivative of the numerator up there? Okay? And so that's basically why I've been trying to instill in you to actually simplify things as you go along with these derivatives, because they'll come back later on. And I guess now is later on. Okay, what else? 3e. Sure, the key idea is for 3 is very simple. F of x is cosine inverse of e to the 2x. So I have cosine inverse of stuff, the derivative of cosine inverse. And by the way, I kept saying this, and I've seen it on some of your exams. Cosine inverse is not 1 over cosine. Let me just say that one more time. Why would we have two different names for the same function? If this would be in fact 1 over cosine, why would we name it cosine inverse or arc cosine, and we'd also name it secant? Would it make any sense? So the idea is cosine inverse is the inverse, but not the inverse of multiplication, but the inverse in terms of functions. So when I take the derivative of cosine inverse, and by the way, considering I've seen it on some of your exams, the derivative of cosine inverse is not sine inverse. And so the derivative of cosine inverse is minus 1 over the square root of 1 minus x squared. Okay? So it's minus 1 over the square root of 1 minus. Now I don't actually have cosine inverse of x, I have cosine inverse of stuff. So I have the stuff quantity squared. So I'll just have e to the 2x quantity squared times the derivative of e to the 2x, which is just e to the 2x times 2. So in essence, I would actually have two chain rules. Is this making sense? Okay. What else? Number 4? Okay, so number 4 says x e to the y plus y e to the x is equal to 1. Oh, I'm glad we actually are talking about this problem. One of the things that I tried to caution you when we started working with these problems is some of you actually applied ln to these and said, well, ln of x e to the y plus ln of y e to the x equals ln of 1, which is 0. What's wrong with that picture? Problem is I cannot apply individually ln's or exponentials to each individual term. I can only apply it to the entire left-hand side and the entire right-hand side. And so if I do want to apply ln's, as it turns out, it'll only make my problem a lot more complicated. Because I'm going to have ln of the quantity x e to the y plus y e to the x is equal to ln of 1. And as it turns out, there's nothing I can do to the left-hand side, because I have an ln of a sum, and there's no way I can actually simplify that in any shape or form. Is that making sense? Is everybody understanding this? And so the only way to solve this problem is to actually directly take derivatives. So if I take derivatives, I'll have e to the y plus x e to the y dy dx plus dy dx e to the x plus y e to the x is equal to 0. Is that making sense? It's two product rules. Yeah? Okay. Now, from here, there's two ways to approach this. We can either solve for dy dx, or we can actually plug in the point we're interested in right now. Which way would you like me to do it? Solve for dy dx? Okay. So dy dx times x e to the y plus e to the x equals minus e to the y minus y e to the x. And so dy dx is equal to minus e to the y minus y e to the x over x e to the y plus e to the x. Now the point we're interested in is the point 0, 1. So if you plug in the point 0, 1 in here, you'll end up with minus e to the first minus 1 e to the 0 divided by 0 times e to the 1 plus e to the 0. And so dy dx will just be minus e minus 1, which gives my equation of that nature. Okay, anything else? The fabled limits. Let me just say one thing, because I've seen this on a lot of your papers. Arctangent of x does not equal 1 over 1 plus x squared. The derivative of arctangent of x is equal to 1 over 1 plus x squared. However, we're not asked to find the derivative, we're actually asked to find the limit. Do you want me to spend any time talking about the first limit?
Yeah, that's one that I didn't get. Would it be the tangent of theta equals e to the x? Is that basically how we could rewrite it and solve?
You're looking at limits, not equations.
Yeah, I know. I have no idea where you can start.
So, the only thing you have to keep in mind is a picture is worth 1,000 words. What is the graph of arctangent? Do you want me to graph the tangent as well? Or can I just graph arctangent? Kind of. Not quite sideways tangent. It's a sideways cotangent, actually. This is the graph of arctangent of x. So what would the answer for 6a be? The limit as x goes to infinity of arctangent of e to the x. Well, what's e to the infinity? Infinity, so this is just arctangent of infinity. Right? This is not really mathematically correct, right? Because I can't really talk about arctangent of infinity, but you're understanding what I'm trying to say, right? What is arctangent of infinity? Pi over 2. Is this making sense? Okay. Now, 6b seemed to be by far the most interesting problem on the test. No. That was basically the problem that got my blood pressure really high. Why? What did I say the number one rule about L'Hopital's rule is? It has to be 0 over 0 or infinity over infinity. Now, the overwhelming majority decided that 1 over ln of x minus 1 over x minus 1 was just 0 over 0 and proceeded to take derivatives. How would this be 0 over 0? It doesn't suffice to just say, so let me give you a quick excerpt of a good portion of the test. Equals 0 over 0, so this is the limit, as x goes to 1, of 1 over x minus 1 over 1. And so if you plug in 1, you end up with 0. How many problems are we seeing here?
Infinity.
First of all, what did I say number one rule in limits is? You plug in the number and you see what you end up with. You plug in 1 for x. Is there any way, in shape or form, you get 0 over 0? Okay, so that's number 1. Number 2, how would you take derivatives at this point and not have 0 here? If you are in fact taking derivatives, why would you only take derivatives of the bottom without actually taking derivatives of the top? So needless to say, that's wrong. How are you actually supposed to solve this? Remember, if you plug in the value, right now you're going to have 1 over ln of 1, which is 0, so you have 1 over 0 minus 1 over 0, right? 1 over 0 is infinity, so the limit as x goes to 1 of 1 over ln of x minus 1 over x minus 1 is equal to, so if you plug in 1 for x, you end up with infinity minus infinity. And what do we say about infinity minus infinity? We need to factor it, we need to do something to get it either 0 over 0 or infinity over infinity, right? What I kept saying about these types of problems is, if you have fractions, the most common way to get rid of that is to actually get to a least common denominator. So this will become the limit as x goes to 1 of x minus 1 minus ln of x divided by x minus 1 times ln of x. Yes? Now what happens when you plug in 1 for x? 0 over 0, and we take derivatives. For those of you that got this far, another thing that I should point out is that we take derivatives of the numerator and then we take the derivative of the denominator. The numerator is relatively easy. It's just 1 minus 1 over x. The denominator, it's a product of two functions. So it will not be the derivative of x minus 1 times the derivative of ln of x, which is something that I've seen on some of your papers. It will be ln of x plus x minus 1 over x. Is this making sense? Another thing I told you about L'Hopital's rule in general is that what you want to do is you want to simplify things before moving along. Because if right now you put in 1 for x, it's still 0 over 0, right? Everybody sees that? But do I really want to take the derivative of x minus 1 over x? Chances are probably not. So if I multiply and divide by x, which just says I'm multiplying and dividing by 1, I end up with x minus 1 over x times ln of x plus x minus 1. This is still 0 over 0. So if I take derivatives now, I have 1 over ln of x plus 1 plus 1. Plug in 1 for x, and you end up with a half. By the way, on purpose, every single one of these limits, as in the 3 of them, I on purpose chose them so that the limits would not be your 3 most favorite choices. 0, infinity, or does not exist. So neither of these actually had a limit of 0, infinity, or does not exist. Is this making sense? Yes.
How did the derivative of x ln of x become
Plus 1.
Oh, this is a product rule.
Product rule. Okay. So let's move on. Do you have any questions from last time? Assuming you actually did any work.
Yeah.
28? I'm guessing your problem's a derivative. One way of dealing with derivatives in general of absolute values is to actually separate them into two parts. So one way of dealing it, if you don't remember what the derivative of an absolute value in general is, the one thing to deal with it is to say the absolute value of x is by definition x if x is bigger than 0 and minus x if x is less than or equal to 0. And so if you look at your function here, 28 on 204, we have g of t is equal to the absolute value of 3t minus 4, which is going to equal 3t minus 4 if t is bigger than 4/3, and negative 3t minus 4 if t is less than or equal to 4/3. Does that make sense? Because at 4/3 is when your absolute value is 0, and before that it has to change signs. Right? So once you have it now, it should be very easy to take the derivative, right? Because you just basically take it on branches. And the key idea that we have taken, hopefully, from chapter 2 when we were talking about derivatives, is that the derivative of an absolute value function, well, the absolute value function is going to look like a v, right? And so when you take the derivative, there's not going to be a derivative at 4/3, right? And so g prime of t is just going to be 3 if t is bigger than 4/3, and negative 3 if t is less than 4/3. So the problem asked for the critical numbers of the function, and so what would the critical numbers be? How do we define critical points? They're the points where the first derivative is 0. Is the first derivative ever 0? Or the points where the first derivative doesn't exist. Right? Points in the domain where the first derivative doesn't exist. Now if you look at your function is defined everywhere. However, if you look at your derivative, it's not defined at 4/3. And so t equals 4/3 will be your critical point. Is this making sense? Okay. What else? 44. Okay, so f of x is equal to x divided by x to the 4 x squared plus 4, and we're looking at the interval between 0 and 3. So if we look at f prime of x, we have x squared plus 4 minus 2x squared divided by x squared plus 4 quantity squared. And so this is just 4 minus x squared divided by x squared plus 4 quantity squared. So far so good? If we set this equal to 0, means 4 minus x squared has to equal 0, so x is plus or minus 2. Right? So this was step 1. Do you remember what step 2 was? We have to figure out the maximum and minimum, right? Which means we just have to plug in, figure out which of those are larger than the other ones. So we're going to test f of 0, f of 2, and f of 3. We don't test f of negative 2 because the interval we're looking for is between 0 and 3. So this is what I was saying on Friday. You have to make sure you exclude all the critical points that aren't in your domain. Or, or I shouldn't say the domain, but the required, the target domain, I should say. I'm very confident you can plug in these numbers and come up with the values and figure out what the minimum and maximum is. Yes?
Yeah, I forgot. Why do we only deal with the numerator of the derivative rather than the denominator?
We're trying to find where the first derivative is 0.
So if we just plug the numerator into 0.
Just think about it. How do you figure out if a fraction is 0? Would the denominator play any role? If the denominator is 0, it doesn't exist.
Okay.
If the denominator is anything else, the only way you can get 0 is if 0 is in the numerator.
Okay. Okay, I get it.
Okay, what else? Okay, so today we're gonna talk about one of the most important, or I shouldn't say the most important, but one of the very important theorems of calculus. And as it turns out, this particular theorem helps prove a lot of other ideas and concepts later on. So it's called the mean value theorem. Now, before I actually get to the mean value theorem, we're going to talk about Rolle's theorem first, and then we'll see exactly what mean value theorem is. So, Rolle's theorem says the following. Let f be a function that satisfies part 1, f is continuous on the closed interval AB. Part 2, f is differentiable on the open interval AB. And part 3, f of A is equal to f of B. Then there is a number, so there is C in the open interval AB such that f prime of C is equal to 0.
What does that CE-AB mean again?
C is in AB.
Huh? Oh, C is in...
It's an element of. This is basically looks like an E, and the idea is C is an element of AB. It means it's in the interval AB. Okay? What is this theorem actually really saying? Well, first of all, notice the conditions we're actually asked. We're asked for f to be continuous on the closed interval, and we're asked for f to be differentiable on the open interval. Also, we're saying that the point where the function starts is the point where it ends. So, let's just look at it graphically. Proof by graphs. I can actually give you a rigorous proof if you really are interested in, which I'm sure you all are. So, let's see. This is A, this is B. Let's say this is going to be f of A equals f of B. Okay? So, my function is continuous and differentiable on the interval AB, which means I start at this dot, I have to finish at this dot, right? Obviously, if I go on a horizontal line, then the theorem is clearly satisfied, right? Because the derivative is 0 everywhere, right? So let's not deal with that particular boring instance. Let's deal with the instance in which, do you want to go up or do you want to go down? Up? Alright. So we're going up. Now, as they say, what goes up must come down. We have to end at this dot, which means I'm up at some point, but at some point I need to come down, right? So I'm up, and at some point I need to come down. Well, I just found my point C, where my first derivative is 0. Is everybody seeing this? Yeah? That's the proof by graphing. Now, this theorem, however, says one thing. It says there is a point between A and B for which the first derivative is 0. What it doesn't say is that it's a unique point, which basically says that I could have my function have a bunch of these points. I guess I missed one. Is this making sense? Yeah? Okay. So, before I talk about the mean value theorem, let's actually look at a problem involving Rolle's theorem. Because what you're going to have to do for homework is you're going to have to do three types of problems. The two of the types of problems you're going to deal with. And by the way, I realized that the homework that I assigned is not the homework that I want you to do. So I'm going to tell you what the homework is. Yes. Yes. Okay, so if I look at problem number 1 on page 210, I'm looking at f of x equals x squared minus 4x plus 1. And I'm looking at the interval between 0 and 4. So the problem says the following. Verify that the function satisfies the hypothesis of Rolle's theorem on the given interval. Then find the numbers C that satisfy Rolle's theorem. Okay? So what should we do? No. Is that enough? The one thing that I don't want to see, nor for your homework, and especially not for your test, is I don't want you to just compute the derivative and figure out where it's actually 0. That's not what the problem says. The problem says verify that the function actually satisfies the conditions. Then find the values. So we have to satisfy the 3 steps. Is f continuous on the interval from 0 to 4? Is f differentiable from 0 to 4? Is f of 0 equal f of 4? Those are the 3 things that you have to verify. Okay? So number 1 and number 2, clearly f is a polynomial. So it's continuous. I don't know why I'm writing with D. Continuous and differentiable on the entire real line. So clearly it will be continuous between 0 and 4 and differentiable between 0 and 4. Does that make sense? Okay. Number 3, f of 0 is equal to 1. F of 4 is equal to 16 minus 16 plus 1. So it's equal to 1. Right? So conditions are met. So now we need to figure out where the first derivative is 0, right? So for that we look at f prime of x, which is 2x minus 4. Set this equal to 0, so I have 2x is equal to 4, x is equal to 2, which means c is equal to 2. Is this making sense? Yeah? Do you want to see another one, or should we look at the mean values theorem? Let's look at the mean values theorem. I answer faster than you did. The mean values theorem says the following. Let f be a function that satisfies number one, f is continuous on a closed interval AB. Number two, f is differentiable on the open interval AB. Then there is a number C in the open interval AB such that f prime of C is equal to f of B minus f of A divided by B minus A. Or if you don't want this, f of B minus f of A is equal to f prime of C times B minus A. Notice that we don't require f of A to equal f of B. Since you liked it before, let's do it again. Proof by graphing. Well, by the way, I'm guessing everybody realizes that this is not really a proof, right? The fact that I'm just showing you a graph and saying here, that's the point. That's just basically kind of like showing you how it, it's an illustration, not necessarily not an actual proof, right? So, again, f is continuous, f is differentiable. This is A, this is B. Would you like f of A to be bigger than or f of B, or would you like it to be smaller than f of B? I'm giving you choices. So let's see, f of A over here, f of B over here, right? Okay, now my function is continuous, right? Which means I start at the first dot, I have to finish at the last dot. I can't lift the pen off the computer, right? How's that? Pretty? Wonderful. What does the mean value theorem say? It says that there exists C such that f prime of C is equal to f of B minus f of A divided by B minus A. Right? If I am to take a straight line between the first dot and the second dot, can you tell me what the slope of this line would be? The right hand side of my equation, right? Everybody sees that? It'll be f of B minus f of A divided by B minus A. What does the mean value theorem say? It just says that at some point my slope will have the same, or my tangents are going to have the same slope as this line. Well, if you look at it visually, I can come up with a few of them. Here's one. Here's another one. Here's another one. That's it. By the way, how do you actually prove this? If you actually prove Rolle's theorem, which is not really hard to prove, Rolle's theorem is actually very easy to prove. The mean value theorem is very simple to prove because it's nothing else but a it's nothing else but a actual skewing of the Rolle's theorem. If you actually tilt your head, in this case about, I don't know, 32.5 degrees, where this line is actually horizontal, that would be actually Rolle's theorem, right? Is everybody seeing this? Yeah? And so that's kind of basically intuitively how you prove it. Is this making sense?
Yeah. Well, so the main difference in Rolle's theorem is that f of a does not equal f of b.
The other way around, you mean?
You have to be different height.
Yes. That's mean value theorem does not require the endpoints to be the starting point to be the endpoint. Okay. So why don't we look at a problem? You want 11 or 13?
Everyone's harder.
I don't know. 13? Okay. F of x equals e to minus 2x, and we're looking at the interval between 0 and 3. So again, we're supposed to verify that the conditions of mean value theorem are satisfied and find point C for which, or find a point C from the mean value theorem. So what should we do first?
It is continuous.
So the domain of F is all real numbers. Your function is an exponential function, which means it's a continuous function, right? So it'll be continuous on 0 to 3. F prime of x is negative 2 e to minus 2x, which is again continuous on 0, 3. Okay, let me not say that because that's not necessarily something we're equipped to talk about. So the domain is all real numbers, and so obviously f is continuous on 0, 3 and differentiable on the open interval 0, 3. Okay? So what's next? What are we actually trying to satisfy? We're trying to satisfy this. So what we're actually trying to find is find C so that f prime of C is equal to f of 3 minus f of 0 divided by 3 minus 0. Is that making sense? Yeah? So f of 0 is equal to 1. F of 3 is equal to e to minus 6. So minus 2 e to minus 2c has to equal e to minus 6 minus 1 divided by 3. Is that making sense? Yes?
Where do you get that minus 2e?
Okay? So now, since you're all versed in all of these types of problems, why don't you tell me what C is? And staring at it is not going to give you the answer. I can guarantee you.
Boy.
Yes.
So the first step would be to define negative 2 after. And then when we divide it over, we have to copy up with it. So now negative 2 is multiplied by the numerator.
So e to minus 2c is equal to 1 minus e to minus 6 divided by 6. Right? I cheated a little bit. You divide by negative 2, right? So instead of 3, now you have negative 6. But I didn't like the negative, so I put it above, which means you switch the order of the terms. Yes? What next? Natural log. So minus 2c is the natural log of 1 minus e to minus 6 divided by 6. Which means that c is minus 1/2 natural log of 1 minus e to minus 6 divided by 6. Hence why I said you can stare at it all you want, you're not going to come up with this answer just by looking at it.
So are we done?
You want the inside that simplified out.
You,
Natural log minus natural log.
I guess you can, but it doesn't really help you in any shape or form. Because again, the problem is you have 1 minus the exponential, and so ln of that is not going to simplify in anymore. It would be nice if we could get rid of this exponential, but you can't. Okay? Is this making sense? Okay, so problem 17 on page 211. We have, what we're asked to find is show that 1 plus 2x plus x cubed plus 4x to the 5th is equal to 0 has exactly one real root. So notice that we're looking at a 5th degree polynomial, right? 5th degree polynomials can have up to 5 roots. What this actually says is that this graph will only cross the x-axis once. How do we prove that without using a graphing calculator? I'll give you a hint. It has something to do with this particular section. First of all, how do we show it has a root? Do you remember how to show it has a root? How do we show it has a root? X equals 0? Well, if you put in 0, you end up with 1 equals 0. Do you remember what the intermediate value theorem says? It has a name. So remember what I said. You probably should know it if it has a name. The intermediate value theorem says what? That if f is continuous, there's a number that f of that remember what the intermediate value theorem says. The point was, again, if you think about it graphically, you start at a point, you end at a point. And so let's say f of a is less than or equal to f of b, then any number between f of a and f of b can be reached by looking at it, at a different point. Okay? Do you remember this at all? I'm guessing no. Okay, so the bottom line was the following. The intermediate value theorem said, I start at f of a, I end at f of b, my function is continuous, so it's got to go on a smooth line. If I make a graph here, pick a value, capital N, between f of a and f of b, there will be some point C somewhere on the graph such that f of c is equal to capital N. That was what the intermediate value theorem said. Okay? Now, we used the intermediate value theorem, and you used it for your homework to show that particular equations had roots. How did we do that? If we pick two random numbers, and their values are different, so for instance, if I look at this particular function, if I put in, so let f of x be 1 plus 2x plus x cubed plus 4x to the fifth. Okay? What is f of 0? 1. What is f of negative 1? 1 minus 2 minus 1 minus 4, which gives me negative 8, negative 6, right? Clearly f is continuous on the interval 0, 1. And so by the intermediate value theorem, f has a root in the interval 0, 1. Is that making sense? Intuitively speaking, your function is continuous. I started negative 6, or sorry, I started 1 and I dropped, no, I said it correctly. I started negative 6, I gotta get to 1. At some point I have to cross the x-axis. There's no other way around it. Right? That's basically what the intermediate value theorem says. Yeah. Oh yes, I'm sorry. This should be minus 1 to 0, minus 1 to 0. So now how do we show it is unique? As in, there's no other ones. Assume there's two of them. That is, let A and B be such that f of A is equal to f of B is equal to 0. What can we say about f prime of x? Well, f prime of x is equal to, what was my function? So it's going to equal 2 plus 3x squared plus 20x to the fourth. Right? Set this equal to 0. How do I solve 20x to the fourth plus 3x squared plus 2 is equal to 0? Well, again, bring back your pre-calculus knowledge, assuming you still have it. Right? If you set u equal x squared, then you end up with a quadratic, which we can solve. U is equal to -3 plus or minus the square root of 9 minus 4 times 2 times 20 divided by 40. So I have -3 plus or minus the square root of -151 over 40. What does that tell us? F prime of x is never 0. Right? And so what is that telling us as far as a conclusion? Rolle's theorem says there is a point. Right? But we found none. So that can only mean that that can happen. Is this making sense?
So there are no roots, or is there still one?
Well, we showed there's one. Right? We're using the intermediate value theorem, we showed there's one. Using the Rolle's theorem, we showed that there can't be more than one. Is everybody understanding this? Yeah? You have to do it for homework. Do you understand it? Well, we showed there's one root, right? So to show that there's not more than one, assume there's two of them, A and B, right? F of A equals F of B is equal to 0, means they're both roots. But what I'm really interested in as far as the Rolle's theorem says is that F of A is equal to F of B. Now my function's polynomial, which means it's continuous and it's differentiable everywhere. And F of A equals F of B, so I can apply Rolle's theorem to find a point C between A and B. But my first derivative is never 0. So I can't find a point between A and B. Is this making sense?
Yeah, what would that look like graphically?
Well, the key idea is that your function's a 5th-degree polynomial. And so, in reality, the graph is just going to be, something like that. Or it could have some wiggles, but the point is they're away from the x-axis. Why is this really helpful? It is extremely helpful because not only we can certainly we can with certainty say that there is exactly one root, which means sometimes you have functions that are very ugly, okay? And you might want to actually find the points where the function is 0. Knowing that there's only one of them is actually very powerful because you can actually zoom into that particular root. Not too long from now, roughly in about a week and a half or so, we're going to talk about something called the Newton formula. And what that does is it actually, if you take out your graphing calculator and you say find the root of this particular function, do you know what it actually does, your calculator? We'll find out in about a week and a half what it does, in the sense that we're going to actually show you a way to find the root. Okay? Now the reason why I'm saying this is because your calculator starts on the premises there's only one root. Okay, and so it's very important to actually know that there's only one in that particular interval, because otherwise you might actually be able to find one root but not find all the roots. Anyway, we'll talk more about this later on. Do you understand what you need to do? So, let's see. New homework.
When we do that, for the intermediate intermediate value theorem, so we always use that.
No. See, what you have to do is, the reason why you need to find 2 points for which your value of the function are opposites. Which basically tells you that your intermediate value theorem is going to come and say, to go from a negative to a positive, I have to cross the x-axis. That's basically what you're looking for. So I just chose 0 and negative 1 because, well, 0 is the simplest one to choose. 0, I would say probably choose always 0 because that's the easiest one to pick. But then to come up with another one, just basically, look at your function. Like for instance, our function had all positives. It was all plus, plus, plus. So I knew the only way to get a negative is to actually look at negative numbers. So I just picked minus 1 because it's just the simplest negative number I could pick. Okay, so homework. This is section 4.2. And we're looking at 2, 4, 6, 12, 14, 16, and 18. So to answer your question, if it's better or worse, your homework, originally you had all the odds as well. You had 1 through 6 and then 11 through 14, which basically said do all the mean value theorem and do all the Rolle's theorem. But since I already did, or I was planning on doing a couple of the odd ones, I figured, I wouldn't want to take the joy, from you to actually do your homework already. So I just added 16 and 18. 18 is exactly what we just did. And 16 is a very interesting problem. 16 will show you, I'm not saying it's hard, okay? 16 will show you why you actually need to make sure you satisfy the conditions of the mean value theorem before you actually take derivatives and plug it in. Because I know your idea, your thought in general is, I'll just plug in the function and find the values and so forth. And 16 basically says, here's a value. Why can't I find it? And the answer is that one of the 2 conditions is not met.
Should you just put condition 1 is not met?
Well, you have to figure out which one is not met.
You just say condition number whatever.
Yeah, basically, but you have to figure out which one and why. You have to give a reason. As I said, it's not actually hard. It's just that